Hello and welcome to today's lesson on ionization and excitation, which is part of the particles and radiation topic in AQA A-Level Physics. So in today's lesson we're going to try and understand the process of ionization and compare and contrast this to excitation. So if we're successful in today's lesson, we should be able to explain what is meant by the ionization of an atom. We should be able to explain what is meant by the excitation of an atom and explain what happens inside an atom when it becomes excited. So in this lesson we're going to be looking at the collisions of electrons with atoms and the energy levels and photon emission part of the AQA A-Level Physics specification. Now the nuclear model of the atom was as follows: that there was a central massive nucleus, and this nucleus contained positively charged protons and neutral neutrons, and if this was to scale, the nucleus is about 10,000 times smaller than the atom, and the nucleus is then surrounded by small negatively charged electrons, and the electrons exist in different orbits like planets around a star, but the atom is mostly empty space. Now, however, there was a problem with this model, this nuclear model that Rutherford had suggested, and that was because James Maxwell Clark stated in his laws of electromagnetism that a charged particle, when it's accelerating, must emit energy or electromagnetic radiation. Now, because the electrons are charged and will be accelerating as they're moving in a circle, they would therefore must lose energy, spiral into the nucleus and destroy the atoms. Now, this process should basically happen straight after the atoms are formed, yet atoms are still here 13.81 billion years after the Big Bang, so this doesn't make sense. So what's going on? Well, the reason why the nuclear model does not make sense is because this model of the atom is not complete. Electrons do not orbit around the nucleus like planets orbit around the sun. This is a simplified model which can be easily understood by everyone, but the nuclear model is incomplete, and in fact it was modified 5 years later by Niels Bohr to account for this mistake. Now, Niels Bohr suggested that electrons do not orbit, rather they exist in energy levels which he named as orbitals. So you can refer to the different regions of electrons as either energy levels, shells or orbitals. All of those names are used in physics. Now, we can imagine the atom to be like a flight of stairs. It was postulated that the nucleus is at the bottom of the stairs and the top of the stairs is outside the atom. Now, we can say that each step is an energy level that the electron can exist on, and the step is called either an orbital, an energy level or a shell. Now, energy levels close to the nucleus have a low energy as there's a high electrostatic attraction binding the electron and nucleus together because the electron is close to the nucleus, whilst energy levels far away from the nucleus have a high energy as there's a low electrostatic attraction binding the electron and nucleus together because the electrons are far away from the nucleus. Now, it's important to note that we call the energy level nearest the nucleus the ground state, and we call the outermost energy level from the nucleus the valence state. Now, an electron can exist on an energy level without losing energy. It will just have the energy of that energy level. Now, this concept is called equipotential, that a particle can exist on a particular plane without gaining or losing energy. But it's important to note that electrons cannot ever exist in between the energy levels. So Rutherford's nuclear model suggested that electrons orbit the nucleus, but this was an incorrect model of the atom. In fact, electrons exist in stable energy levels around the nucleus. So the rules of the Bohr atom are as follows. Number 1, electrons can exist on different energy levels or orbitals, but not in between. The ground state or level is the shell closest to the nucleus. The highest level or state, which is the most outermost, is called the valence shell from the nucleus. Electrons can be instantaneously transported to higher levels, but that requires energy to be inputted into the atom. And electrons can instantaneously transport to lower levels, but that gives out energy to the surroundings. And these are the basic fundamental principles of quantum mechanics. Now, when Bohr mathematically derived his model of the atom and compared it to hydrogen, he found that this model explained hydrogen's interaction accurately. However, when he compared it to larger atoms, the model was not completely correct. So it actually showed that the Bohr model needed further amendment. Now, the Bohr model only works for hydrogen because it only considers the interactions between one electron and the nucleus. Now, any other electrons in the atom will repel other electrons and then change the value of the energy level. Now, the Bohr model does not consider these extra interactions, so it doesn't work for atoms other than hydrogen. But luckily for us, we just consider the Bohr model to work for all atoms in A-level physics. So let's look at this particular example. This atom has 3 possible orbitals. So this means there are 3 possible energies that electrons can exist on within this particular atom. So the electron could exist here in energy level 1, or energy level 2, or energy level 3. Now it's important that the shell that represents the innermost shell is called the ground state, and the shell that represents the outermost shell is called the valence state. Now it's important to note that for each level the electron requires a certain amount of energy to exist on that level. Now the lower the energy, the less energy is needed, because it's easier for the electrons to exist on that level. Now this happens as the electrons are closer to the nucleus and feel more attraction, so are more stable. So for example, if we just give some nice easy values, okay, we could say that you need 20 joules to exist on energy level 1 and 70 joules to exist on energy level 3. Now if you wish to move an electron up in energy level, it needs to be given the exact right amount of energy to move it to the correct level. If more or less energy is given than the energy jump requires, it does not happen. So for example, if you wanted to jump from level 1 to level 2, you would need to give the electron 20 joules in this example. To go from 1 to 3, you would need to give it 50 joules. And if you gave it anything different, not the exact amount, the jump wouldn't happen. Now just to clarify, this is only true if it's a photon which is exciting the electron. A colliding electron can actually have more than the exact energy level difference to cause this excitation. So it's just an important difference to know about. So when an electron is moved up in energy level by being given energy, we say it's being excited. So the process of moving an electron up in energy level is called excitation. So in this example, if we just consider photons and not colliding electrons, if an electron was given 23 joules in this example, nothing would happen as it's not an energy level difference between the levels. Now if we gave it 27 joules, nothing would happen as it's not an energy difference between the levels. And again, if we gave the electron 32 joules, nothing would happen as it's not an energy level difference between those different levels. But remember, this is only for photons, not for colliding electrons. Now if we gave an electron 30 joules in this example, it could move from level 2 to level 3 as it's an energy level between those particular values, because 70 minus 40 equals 30. So this is an important idea. Now to work out if excitation occurs with a photon, you've got to work out the energy level difference and see if the photon has that exact energy. Now the reason why the electron needs to have this exact energy to move is due to its wave nature. So if the electron is switching its wave frequency, similar to how a standing wave is formed at discrete frequencies on a string. Now the fact that either the photon supplies the energy or doesn't supply the energy for excitation is further proof of the particle nature of radiation. So another example, as well as the photoelectric effect, for the particle nature of light is the excitation of electrons in atoms, because only one photon can excite one electron at a time. So it's very similar in this instance to the photoelectric effect. Now when the electron is given just the right energy from the photon to move between shells, then the electron disappears off the original shell and reappears on the new shell. It doesn't actually travel between the shells, so it could go from 1 to 2 like this, and we call this idea a quantum leap. Now what's happening is the electron standing wave is actually instantaneously changing its frequency, which we observe as a movement from level 1 to level 2. Now if the electron receives more energy than the energy needed to leave the outer shell, the top level, the electron will leave the atom. Now this process is called ionization, and the energy given to an electron by a collision with another particle can cause this, and the most common example of this is another electron. So this energy given to the electron by a collision with another electron can leave it to make it leave the atom, which is ionization. Now it's a common misconception to think that the electron is ionized when it reaches the outer shell. No, it needs to leave the outer shell and reach the ionization level. Now unlike excitation for a photon, ionization can occur when the energy level difference or higher is given by the photon, and any excess energy goes to the kinetic energy of the electron emitted. So again, in ionization, not all of the kinetic energy of the electron will need to be passed to the atom in the particular collision. So this is similar to the photoelectric effect. However, the photoelectric effect is a particular type of ionization. The photoelectric effect is the ionization of electrons from a metal surface due to the absorption of electromagnetic radiation. Now, ionization in general is the emission of any electron from any atom due to energy being given to it. Now, as we mentioned before, okay, the idea of the energy given to the electron to ionize it is by collision or via a photon. So ionization can be considered an extreme form of excitation. So excitation is when electrons move up energy levels. Excitation occurs when the electron is given energy, most commonly a collision with another electron, but it can also be given by a photon. Now, excitation only occurs when the energy received by the electron is the exact energy level difference when it's a photon exciting it. Now, excitation is instantaneous and proof of the particle nature of light. So let's look at this particular example. You could have excitation by colliding an electron with an atom, and at that point it will give the atom enough energy to move an electron from one shell to a higher shell. Now, ionization is when electrons move up energy levels and then leave the atom completely. Ionization occurs when the electron is given energy, and this is most commonly a collision with another electron, but it can also be an absorption of a photon. Now, ionization occurs when the energy received by the electron in the atom is the exact energy level difference or greater. So when ionization occurs, the electron is considered to be free. So in this example, ionization could be caused by the collision of an electron with an atom. This will then give the atom enough energy to release an electron out of its structure. So we can look at the difference between excitation and ionization. Now, in ionization, we make an ion. Now, an ion is a charged atom, and the number of electrons in an ion is not equal to the number of protons. So an ion is formed from an uncharged atom by adding or removing electrons from the atom. Now, adding electrons makes the atom a negative ion, removing electrons makes the atom a positive ion. So the process of creating ions is called ionization. So alpha, beta, and gamma radiation create ions when they pass through a substance and collide with the atoms of that substance. Electrons passing through a fluorescent tube create ions when they collide with the atoms of the gas or the vapor in the tube. So ionization is caused by the collision of a particle with an atom or with another photon being absorbed. Now, the normal particle that collides with the atom is another electron, and this will give the electron orbiting the nucleus energy, and an electron colliding with an orbital electron can also cause excitation. Now, what happens is the kinetic energy of this first moving electron is passed to the second electron inside of the atom. So this causes that second electron contained inside that atom to either be excited or ionized. Now, this can actually mean that all of the energy of the first electron can be passed on to the second electron. So it means that first electron could stop moving. So let's just clarify. Both ionization and excitation are caused by an atom gaining energy via a collision with a fast-moving electron. Now, we've previously considered the absorption of photons, but in this part of the lesson, we're just going to consider ionization and excitation occurring due to a collision with a fast-moving electron. So when they have a collision, this fast-moving electron is moving in an electrical current, and this collision causes the energy to be transferred from this fast moving electron to the atom. Now, the electron can transfer all of its kinetic energy to the atom and stop moving and become stationary. Now, but the free electron only actually has to transfer enough energy to the atom to actually excite it. So this means it could actually continue to move after the collision. But let's consider what happens to this excited atom. So when energy is transferred to the atom, this can cause the atom to be excited. The atom will then eventually relax and release a photon of energy corresponding to the energy level difference of two energy levels inside its structure. Now, in this particular example, the electron has stopped moving, so if we were measuring the current in the particular situation, the current would dip if excitation is occurring. But just remember, if the colliding electron does not have enough kinetic energy to cause excitation, it will be deflected by the atom with no overall loss of kinetic energy. energy. But always remember, an electron inside that atom will absorb the exact right amount of energy to move between two levels after colliding with that free electron. That will contain either the same energy or greater energy than that is required for the electron inside the atom to change energy levels. Now, as energy is conserved, the energy gained by the electron inside the atom equals the energy lost by that free electron that's collided with it. Now, the free electron's kinetic energy after the collision is the same as it was before, minus the energy transfer to excite the electron in the atom. Now, in ionization, it's a similar process. So you can have an electron, and an electron can collide with an atom and cause it to be ionized. Now, this occurs if the fast-moving electron transfers enough energy so an electron can have more than the ionization energy of the atom. So this will cause the atom to release an electron due to the ionization process. So whilst the original electron could be not moving after the collision, another fast-moving electron has been replaced from the atom to then release it. So this second electron can replace the first electron moving round the circuit so the current won't dip. Now, in addition, in ionization, the original colliding electron doesn't actually have to transfer all of its energy to the atom, so it could still be moving after the collision takes place. Because remember, the conservation of energy still applies in this situation. Now, any energy above the excitation or ionization levels remains as kinetic energy of the electrons, or it could be the kinetic energy of the recoiling atom after the collision. Now, when an electron collides with an atom to be ionized, because we definitely will have electrons emitted from the process, no observed dip in current is observed. Now, in reality, the energy needed for electrons to exist on an energy level in the atom is very small if we express this value in joules. So therefore, we use a different unit to make energy level calculations easier. We use the electron volt. Now, the electron volt is a unit of energy and is equal to the work done when an electron is accelerated through a potential difference of 1 volt. It comes from the electrical potential energy store equation. So for a charge Q moving through potential difference V, the work done is equal to QV. So therefore, for an electron moving through 1 volt, work done is equal to QV. So it's 1.6 times 10 to the minus 19 coulombs times by 1. So therefore, the work done is 1.6 times 10 to the minus 19 joules. So that gives us a conversion factor that 1 eV is equal to 1.60 times 10 to the minus 19 joules. So let's look at an example of converting between electron volts and joules. So one of the energy levels in helium is expressed as 12 eV. Convert this into joules. Now remember, your conversion factor is 1.6 times 10 to the minus 19, and as we're moving back into SI, you multiply this by the conversion factor, so you get an answer of 1.9 times 10 to the minus 18 joules. Now if you wanted to go the other way and convert one of the energy levels in helium from 1.78 times 10 to the minus 18 joules into eV, you've now got to divide by that conversion factor. So you do 1.78 times 10 to the minus 18 divided by 1.60 times 10 to the minus 19 equals 11.1 eV. Now the process of excitation is moving an electron up to the energy level but not leaving the atom, and this requires energy to be placed into the atom. Now again, this can only happen at the energies which correlate to the differences in energy levels. So the energy needed to excite this electron to level 3 is 1.9 eV, because the difference between 6.2 eV and 4.3 eV is 1.9 eV. Now to work out if excitation occurs, you've got to look at the energy level differences and see if the photon has that exact energy level difference. Remember, with an electron, you don't need that exact energy level difference, it's only a minimum value. So, when excitation occurs, the colliding electrons make an electron inside the atom move from an inner shell to an outer shell. Energy is needed for this process because the atomic electron moves away from the nucleus of the atom, and it comes from the kinetic energy of the colliding electron. Now, excitation energy is always less than ionization energy of an atom because the atom is not completely, so the electron is not completely removed from the atom when excitation occurs. Now, when a colliding electron hits the inner shell electron, electron to cause excitation, it loses its kinetic energy equivalent to the energy level difference between the two levels. So the current flow due to the flow of electrons through the gas goes down, which is how we can work out what the excitation energies are. Now this doesn't happen in ionization, as whilst the colliding electron can stop moving, another electron is released by the atom to continue moving in a current. So in this particular example, we can see energy values which an atom absorbs, which we call the excitation energies. So we can determine the excitation energies of atoms in a gas-filled tube by increasing the potential difference between a filament and an anode and measuring the PD when the anode current falls. So in this example, we have two prominent excitation energies of the mercury atom, one at 4.9 eV and one at 5.7 eV. So it would mean that if we placed a potential difference through a gas of mercury, the current would dip but not completely go to zero at 4.9 volts and 5.7 volts. Remember, it doesn't go completely to zero because all of the electrons aren't stopped moving when they cause an excitation due to collision, because it has to just be that energy level difference or above for a colliding electron. So what have we learnt in today's lesson? We've looked at ionization and excitation and started to look at the idea of ionization and excitation in a fluorescent tube. We looked at the electron volt and how to convert between EV and into joules and vice versa. And if we've been successful and learnt in today's lesson, we should be able to explain what is meant by the ionization of an atom, explain what's meant by excitation of an atom, and explain what happens inside an atom when it becomes excited. So I hope you've enjoyed today's lesson on ionization and excitation in the particles and radiation topic in AQA A-Level Physics. Thank you very much for listening and have a lovely day.